Here we have Cantor's intersection theorem. What does it say? So in Cantor's intersection theorem, we have a sequence Kn of non-empty compact sets that form a nested sequence, a nested decreasing sequence. What does this mean? This means that for every k, for example, that was k1, k2 is going to be contained in k1, k3 in k2, and so on. Okay. In a situation like this, what the theorem says is that the infinite intersection is non-empty. This is not completely obvious because as we go to infinity, it may or may not leave anything behind, okay? The fact is, because they are non-empty compact subsets, there will be something left, okay? That's the whole point of the theorem. So how to prove this? Notice here, we have two hypotheses. The sets are three, non-empty, they are compact, and they are nested. Okay, so we have to use all three. So proof. Let's, to be clear, let's write it here. K1 is the largest. Okay, and we have that K1 contains K2, contains K3, and so on. Okay, let's proceed by contradiction. Let's assume that the intersection of the Kn from 1 to infinity is actually empty. Here, the main property we have about the Kn is that they are compact. Okay, so we actually need to use the compactness. The way we are going to do that, we need to connect that with some open cover somehow. Okay, and because these Kn are closed, the easiest way to do that is to work with the complements. Okay, so that's the general strategy. We are going to define new sets Un that are the largest, K1, minus Kn. Okay, there are two notations for the difference of two sets. We can write it with the slash, or we can write it with a negative, K1 minus Kn. Okay, this means the points in K1 such that they are not in Kn. Okay, or if we want, this is K1 intersection with the complement of Kn. These are different ways to say it. Okay. All right. So once we have the UN defined, something we can observe is that when we take the union of all these UN, this is K1 minus the intersection of the Kn. Now, because we are assuming that this intersection is empty, this means that the union of all the UN is equal to K1. But now notice that the UN are open relative to K1. This is important. They are open relative to K1, okay? Because they are the complement of a closed, okay? So what do we have here? Then we have here that the UN is an open cover of K1. You see here we are already connecting with the compactness hypothesis. Because it's an open cover, it's an infinite open cover, then by compactness, well, there is a finite subcover. There exists a finite subcover. Let's call it UN1 through UNN. Okay, this means that I'm picking a finite number of indices that give me a cover of K1. Let's say, just to be clear, that the NJ are in increasing order. So N1 less than N2 and so on. Okay, just to, so we are in the same page. Notice that we have, when we take the union of all these Nj, okay, from 1 to N, what happens here? Well, the union is equal to UN capital N. Okay, how do we know this? Because the Kn are nested. Okay, and as N grows, the Kn becomes smaller. Okay, and that means that the UN become larger. So the union of the UNJ is going to be the largest of those sets. So this implies that K1, which is the union of the UNJ, because the UNJ are a subcover of K1, okay, the way we define them. This, well, let's actually do all the steps. So because it's an open cover, if I go all the way to infinity and it's compact, I take a subcover all the way to N. There we go. Now it's all fixed. The first index is N, the second index is J. And now this union, I know it's the largest of those UN. Okay, we said it was UN capital N. Here we are basically set, because the way we defined UNN was as K1 minus KNN. Okay, this was by definition. And now when I look at those two things together, you see I have that the first one is saying that K1 equals UNN, and the second one is saying that UNN equals K1 minus something. So that means that KNN must be empty. And this is a contradiction, because we were assuming that all the KNN were non-empty. And now we have used all the hypotheses. Notice, if you are trying to prove a theorem and some hypothesis, and you're not using some hypothesis, be careful, okay? You may need to revise the argument, because there may be some tricky point that you are missing. There is a more general version of this theorem that we are not going to prove. The proof is on the book, but it's very similar to what we just did. That says that if we have a collection K alpha, notice that here I'm not saying that it's a countable collection of compact subsets, well, of a metric space X, such that the intersection of every finite subcollection of the K alpha is non-empty. Okay. Then the intersection of the K alpha is non-empty itself. Now, here, notice that this hypothesis here that may look a little strange, such that the intersection of every finite subcollection of the K alpha is non-empty. This replaces the nested decreasing sequence that we had before, okay? So if you have a nested decreasing sequence, that in particular satisfies that the intersection of every finite subcollection is non-empty. So this is just a more general version of the same theorem here. The point is that we are not assuming neither that the sequence is nested, neither that is a countable sequence.